Good afternoon, folks. I've been called lots of things, but not a grave robber yet, so that's a new one. I'll put that on the business card. Brilliant. So where do we start with batteries? We talked a lot today about electric vehicles and how they do a lot for us around decarbonisation, around reducing the noxious emissions that we see from cars today. But at the heart of that is this lump here, the battery. And just to put that in perspective, automotive manufacturers are really good at hiding this under the car somewhere so you don't spot it, but it weighs between 400 and 800 kilograms. So it's good half a ton's worth of stuff in there. A small one will cost you about £5,000 bill of materials, and a large one will cost you about £20,000 bill of materials. So it's a very significant driver on the vehicle, and whilst we're selling lots of those vehicles, we can expect to see a lot of these back in about 8 to 10 years' time coming into the waste stream. And where the value is in that, about half of the value is in the cells, the fundamental building blocks of the battery that sit within it, and the other half is in converting those cells into the kind of structure that you see on the slides behind me. And when you look inside the cell, that's made up of a number of different components, but what you'll see from here is that about half of the value of the cell, which is the bit that does the job in there, is the cathode material which goes into it. So it's just one part of that electrochemical system. And within that cathode material, I'll show you in a moment, but what you've got there are some active electrochemical powders coated onto thin foils, typically aluminium, and the value is all in that grey goo that we coat onto that aluminium foil to make the cathode itself. So when we make a battery, we start off with a lump of rock, and somewhere out in the supply chain, it gets pulled out of a mine, it gets refined into raw materials, and those raw materials then get combined to make the active powders, the electrochemical components of our batteries. And to be clear, what that is typically are things like graphite, usually milled to a very fine particle, micron-sized, sometimes nano-sized in texture. And we're typically working with metals like nickel, like cobalt, like manganese, aluminium, iron, various phosphate materials. And a very significant chunk of the value creation here is in the conversion of those raw elements through to these active powders in a form which is going to be usable. One popular misconception, there's no rare earth in lithium-ion batteries. There used to be in nickel metal hydrides, there's no rare earths in batteries. These are engineering metals that we're working with. Once we've got those powders, we coat them onto thin foils called current collectors. And the way that you then build a battery from those foils is you either roll them up like a Swiss roll and stick them inside a can, or you stack them like a lasagna and put them inside a pouch. And what you end up with is the contact between the surface areas of all of those components allows for an electrochemical reaction, and that's how you store the energy and that's how you recover it. We then take those cells and we assemble them into modules, which are sub-packs, if you like, and we do that to keep the voltage of that component below safe working limits, below 60 volts typically, and keep the weight light enough that we can move it around a factory. And then finally, we put those modules into the battery pack, which is the big lump that you saw on the first slide. And every step of that process costs money and adds value. Roughly speaking, as I said before, half of the value in the pack is the cell, and the other half is the conversion of the cell into the pack with all of its management systems. So at the end of the life of that pack, what I'd really like to do is find a way of reusing it. And ideally, what I'd like to do is retain the maximum value that I've embedded in that product. So clearly, if I can take my pack and use it as a pack, that's a very nice place to be. And that's why you'll see a lot of talk around second life of batteries, taking a pack that's 20% degraded in its automotive application, and sweating it for another 10 years in a more benign operation like domestic energy storage. But to be able to upgrade it to run back into a vehicle is unlikely because the kinds of damage that's going on inside that cell is both mechanical and electrochemical. It's not something that you could go in and fix very easily. At the next level of aggregation, what I might be able to do is to remanufacture battery packs. So if I've got one module in the pack that's not working so well, then perhaps I can go in and strip the pack out and replace one of those modules and keep the rest of the pack running for a longer period of time. But failing that, then I'll move into a recycling route and I start to strip the cells out of that module to see if I can reuse those. I take the cells apart to see if I can get back down to the electrode materials, and then I could perform some refining operations that would recover those electrode materials and turn them back into the component elements that we started with. But clearly, every step of that chain costs even more money. So I started with an expensive process, and every step that I take back down the process costs me money. And then as I go back up the chain to build it back into the battery that I want, I'm adding money at every step along the way. So that process of recovery and recycling and reuse is a relatively expensive one. And at the moment, if you look at the price of doing that versus the price of using virgin material in the markets we have today, it's considerably cheaper to use virgin material than it is to recover the components from the battery. So the main drivers that we see towards recycling in the first place are coming from regulatory and not economic conditions. Fast forward 20 years when some of the elements that we're using are a bit rarer, maybe that will change. But in the first era of battery recycling, it's likely to be regulation that drives recycling to this degree rather than economics. And just to put a scale on the problem, we said earlier, the UK sells about 2 million vehicles a year. It varies from about 1.7 to about 2. And most of the industry forecasts that we're looking at say that we could get to about half of those sales being electric vehicles or plug-in hybrids within about a decade, so certainly by around 2030. So if you then multiply that up by the mass of the battery and the amount of material in there, that means we've got 500,000 tons of batteries are going to start coming back into the waste stream about 8 to 10 years from that point. And the value of the materials that went into those batteries is going to be worth about £1 billion per year. And that's the point at which we start to move from being a waste disposal problem to being a value recovery problem. The challenge that we've got is that we simply don't have processes around us today that can access those materials. The majority of lithium-ion batteries today, the kind of thing that you've got in your mobile phone or laptop, goes for recovery. The type of batteries we use today have very high cobalt content, and cobalt's expensive, so the cobalt is recovered from that cell. The lithium, the copper, the aluminium, the electrolyte, the pouch material are typically incinerated, and they're mostly going into breeze blocks these days. So we need processes which will allow us to access those materials more efficiently and which will allow us to recover the value for them. About a year ago, a good friend of mine, Sam Haig from Axion, stood up next to me at the Can We Put the Z into ZEV event that was organised through the APC. And he talked about this challenge. He talked about how we're going to make this work on an industrial scale. And over the last 12 months, we've been working with him and his team in a project called Amplify that's looking at exactly this issue. And they've spent a lot of time mapping the value chain to understand who are the actors, what are the economic drivers for them to perform, who's going to lose money in that game and who's going to gain money in that game, and how do you get an economic system as well as a technical system which can join together and make this work. And you can see from the sort of life cycle that there's a whole bunch of different actors that have to come together in this to work. There's research to actually get to the processes that we need in order to be able to scale them up. The material suppliers need to be able to accommodate recyclate within their manufacturing streams. And then we have to take that through into the pack design, the vehicle manufacturers, into the end users, create a second life market, and then have a route back into recycling. And actually, I think one of the biggest challenges that we face here is the time it's going to take to put that infrastructure in place at a scale that will deal with 500,000 tons of material per year. But key to making it work is about retaining the value in the system. So what you can see here is that in the work that we've been doing with Axion, they've been looking at going right the way down to the material recovery stage, but then seeing if they can feed that material in at the cell manufacture stage rather than taking it all the way back to its raw elements. And they've been looking at how you influence the design of a battery pack to make the recovery of the material as quick, as cheap, and as easy as possible. And some of the things that we've looked at through that program, they've mapped the collection schemes. If you think about where we are today, if you take your scrap vehicle, you take it to a scrapyard, your scrapyard's probably 10 miles away maybe. When we start to look at having to repatriate batteries to centres, we're looking at taking a component that weighs half a tonne and repatriating it perhaps 50 or 100 miles to get to centralised recycling facilities. And when we get there, we need to assess whether the battery is safe, whether it's worthy of a second life, and what we're going to do with it. So one of the first things that we've got to do before we can recover the materials is actually make that battery safe. It's to discharge it. And one of the things that Axion have been doing over the last 12 months is to look at methods that we can take a battery in completely unknown state. It could have come from a crashed car. Half the cells could be disconnected. And they've been developing solutions into which you can dip the battery, which will safely and slowly discharge it until it contains no electrical charge at all. And at that point, you can drop it into the shredding machine that you see next to me. That then returns it to small components, and they've got some fantastic technology for sorting those to separate out the different bits that we can start to reclaim the value. And coming from that is a whole load of stuff that's taking us into how do we design for recyclability in the first place. I'm not going to go through these in details, but you can see there's parts around control, there's things about the choice of materials we use, how we join them together, and the design, not just for how you build a battery, but how you take it apart. Most of the batteries on the road today are a complete nightmare to take apart. They use adhesives to put the cells in place. Lots of the parts are welded together, and they're very inaccessible. And working with Axiom, we've been able to come up with cell designs, and module designs, which are actually as cheap to build, but are recyclable. And secondly, they've been looking at the processes that we need to access those materials. How do you make the battery safe? How do you disassemble it? As you saw on the first slide, all of these batteries are fundamentally different in their size and in their construction. So we actually need data coming through from the manufacturers to help recycling centers have robotic disassembly that means that they can very quickly process those materials. Then we're looking at recovering, and then we're looking at upgrading and reusing those materials. So the field is moving quickly, but it needs to. We've only got about 8 to 10 years to get these recycling processes in place at half megaton per year scale. And it takes 3, 4, 5 years to build those plants. So the quest for research on this is an urgent one. We lack the processes to recover many of these materials. So we're working hard on that. I mentioned earlier Axiom is. You've seen the work that Alan and his team up in Birmingham are doing. There's a lot of work on the academic level. Next thing we need to do is look at how we industrialize that. So thank you very much.